Thanks, folks. Today we're going to talk about a new feature that we recently added to PyMC Marketing around discrete choice models. Discrete choice models are a kind of species of models that stem from econometrics and industrial organization. And we've adapted a Bayesian flavor of these for the PyMC Marketing package. Preliminaries, just briefly, my name is Nathaniel Forde. I'm a data scientist with Personio. You can find code at my website, which you should be able to visit if you follow the QR code, or look at the PyMC Marketing docs. The broad pitch of this talk here is that product design and product strategy sort of drives the success of various businesses. And you need to be very careful when you sort of think about what the next development trajectory is for your product. And this can be a cost-intensive exercise. And PyMC Marketing will allow you to simulate sort of product interventions or strategy shifts safely and learn the expected impact of those new product strategies. So the agenda of this talk is sort of 5-part. We're going to give a little bit of broad Bayesian background on the choice scenario setup. We'll talk about what the choice data looks like. I'll speak briefly about what PyMC Marketing is, and then I will sort of describe a problem. I will talk about the multinomial logit model, which is a type of discrete choice model that has some deficits. But going into the deficits, we'll highlight what we need to fix to do discrete choice well, which I will then sort of give you the solution to the problem I've just displayed by showing the nested logit model and how to encode market structure in your consumer choice modeling. And then it will invite you to build your own models with PyMC Marketing. So the choice setting here. So I don't know if this is as familiar as it is in Germany as it is in Ireland, but I used to read these books a lot when I was a kid. These are choose your own adventure, sort of branching path books. You would get to read one page, it would allow you to make a choice, and you'd go to the next page. These were great, lots of fun. What I loved about them, they had like discrete possible endings. You could explore all the paths. It was deterministic routing, preferred endings, and you could peek ahead. You could cheat and figure out what was the best outcome for you, which I regularly did. But as you grow up, you eventually become Bayesian. You realize that there's a continuum of possible endings. You have no possibility of complete oversight or survey. There's at best probabilistic choice over those paths. And the only certainty, if any, is in expectation or the breadth of possibility. Okay, so this is the Bayesian formula that you've probably seen a million times. I've got a slight gloss on it. So that theta parameter in that formula there, the probability of theta and the probability of y given theta, is a bit dry. So what I want to do is sort of, to motivate it a bit more, is that this theta is indexed to w. And instead of thinking about a vector of parameters, you think about the vector as describing states or describing attributes of the possible worlds. So what you're learning when you fit a Bayesian model is you're making an inference to which is the most plausible world given the data. So you learn the set of parameters that are the best descriptions of one of the possible worlds, conditional on the data you have to hand. That's the traditional backwards inference, so to speak. If you want to push forward, you can also ask another question with Bayesian inference of what plausibly happens at nearby worlds, or what happens at your world when you intervene on it. So instead of thinking about the Bayesian setting in like this dry sort of mathematical formalism of like theta, think about it as theta, which is fed through a function which describes attributes of your world and relationships in your world. And this gives you the probability of your data y at a given world. And so once you have that, you can rank these worlds in terms of their likelihood. So you can say which are the most probable worlds. The other way you can think about these possible worlds, or these sets of possible worlds, is that worlds can be ranked in terms of their desirability as well. And when you know the attributes of the data or the products or the choices you're making, you can estimate their desirability. And their desirability is going to inform how people make choices in those worlds. So the theory of choice that is sort of sitting behind these models is, as I said, drawn from econometrics. It's this notion of revealed preference, where we look at the choices people make, consumers in a marketplace, for instance, And we sort of have this theory that they're trying to maximize, so their utility perhaps, or expected value. Or maybe they're just driven by sort of impulses and whims, or the effects of marketing, as every CMO would like to think. But the broad pitch here is that every path taken, every choice made by a consumer or an actor or a firm can tell you something about what are the attributes of those choices that tempt or repel human actors. And the way we formulate this in a mathematical formalism is like this. So the equation here at the top is sort of the pivotal one. We think about the utility that accrues to any given good, and those goods are described by their attributes. These x1 and x2 here are attributes, and some sort of relationship to the choices made. So the way this is formatted here is that we have linear relationship. So there's an intercept term alpha, there's a beta coefficients beta 1 and 2. These are all fed into, the blue terms are estimated to derive a utility score, which is pumped through a softmax transform and then pumped into a categorical distribution. That's the mathematics, the mathematical structure, the functional relationships between the observed attributes of those products and the choices that are made in the market. And what we're doing when we fit a Bayesian discrete choice model is to try and infer what are the best values for those blue parameters conditional on the observed patterns of choices we have seen in the data. Okay. And that allows us to sort of compare different goods. So if you are walking through a deep, dark cave and you come across this choice, this bifurcated choice in the cave, and you see on the one hand there's a light shaft and silence, and on the other there's a glowing fire and echoes of conversational noise. Are you, as an individual consumer or cave dweller, drawn towards the fire and other human contact, or do you retreat into the deep, dark hollow of the cave? It's a choice for you to make, but also the more general choice is what will the average cave dweller do? And when we are working in PyMC Marketing, we want to figure out what are the actions of the average consumer or the average cave dweller. We need to figure out how important is light, how important is silence, or attributes of more traditional products. So PyMC Marketing, for those that don't know, is a sort of Bayesian marketing analytics package offered by PyMC Labs. It covers a lot of use cases from media mix modeling to customer lifetime value and other varieties of consumer choice modeling. It's sort of causal inference ready for the most part. It's a modern Bayesian engine for flexibility, and it's got sort of intuitive syntax and powerful underlying models. This is the choice data set, or a choice data set. The key thing to note here is that the dependent variable is the observed choice, the observed product. So in this case, the data set we're looking at here is a data set of heating systems. So there's gas central heating, there's gas radiators, there's electrical central heating, there's electrical radiators, and there's a heat pump. So these HP, EC, EOR. And we have those described in terms of their attributes. Here, the important attributes are installation cost, IC, and operating cost, OC. So we want to take this data, which is a full description of all the products in the marketplace at any given time, and try and predict the choices made by the consumer class. And we want to figure out what are the sort of import of each of those features or attributes as inferred from the data, so that we can then forward simulate how changes to those attributes can inform us about future product decisions. So the feature that we've added to PyMC Marketing allows you to fit these two classes of models I'm going to discuss. The multinomial logit model with a sort of Wilkinson-style formula interface, but also the nested logit model with the same type of API. This allows you to fit sort of alternative specific attributes and figure out how important those are. So price, quality, brand effects, but also sort of individual consumer fixed attributes. So your income doesn't necessarily change when you're looking to consider a purchase of a car or a boat. Your income is the same, and one is feasible and one is not. We've also built in some sort of causal inference routines into this modeling because it sort of naturally fits the model class. Okay, so I'm going to first talk about the multinomial logit model, which is a classical one, and it is problematized by this notion of It's a problem in the literature called the independence of irrelevant alternatives. So the multinomial logit, as before, it's like a softmax transform. You push your data through a softmax and you get out from a utility vector of a utility per good, a probability of choice for each of those goods. And then you use those probabilities of each of the goods to sort of infer the market share of each of those goods. It's simple, perhaps a little bit too simple, but you fit it in PyMC Marketing like this. You specify the formula interface for the utility relationship or utility equation for each of those goods. You pump it in this sort of one-liner through the ML logit estimation routine, and it will give you like all the standard diagnostics of a Bayesian model, as you would see with PyMC. Below here you see like these are trace plots, and I think in the context of this talk, what I want to emphasize here is that these trace plots are like journeys through possible worlds. Like each arrival or each point on this sort of time series or sort of scale is a new value for one of the parameters in the mathematical formula that you saw before. And what you're doing when you're estimating a Bayesian model and deriving the posterior is sampling across the posterior and looking at sort of realizations of that vector of parameters that go into the mathematical formula that define the utility relationship in the market. So the problem with the multinomial logit model is purely one of the mathematical structure. So this is the softmax transform, or rather the two softmax transforms. If you were to compare the market share of two goods, you only ever compare in a bivariate way. You compare one good versus another, and you're ignoring the rest. And that's kind of a problem because it implies an implausible counterfactual in a very real world circumstance. So the canonical example here is if you have a market share which is 50% red bus and 50% car. If you introduce a new blue bus to the marketplace, which is the same in all other attributes as the red bus except for color, the multinomial logit model will imply a new market share of 33% for each of the goods. That's because this model will cannibalize equally of the market share of all prior existing goods. And that should be a problem, or it should be intuitively a problem, because it means that the competition in this marketplace is sort of seen as equal across all the goods. There's no structure of the competition. A car user is just not randomly going to decide to use a bus when a new bus comes on the market. So the point here is that this market ignores very real and plausible attributes of the market structure systematically because of the mathematical formulation. So so I mentioned that this is causal inference ready. So this is how you would sort of make a counterfactual inference with PyMC Marketing. You define a new data set, which is similar to your old one, say, but in this case, you've added a 50% multiplier to the installation costs of the electrical central heating and the electrical radiator system. And I think maybe this is a little bit small to see, but what you see in these three columns is the original market share under the real data, or under the observed data, the new market share under the counterfactual policy of a new price setting, and then what you see here is relative percentage change. And the thing I want to call out here is that the goods for which we have not intervened on have all seen an 8% rise in their market share. So this is the cannibalization problem I mentioned. Cannibalization occurs, but it occurs equally across all goods in the market. So this is an implausible counterfactual in most complex markets. So there's not to say that there's no use cases for the multinomial logit. If you can add enough sort of covariates to your multinomial logit model that it already partitions the market in such a way, you can use that. But you need to be careful when you're using it because, like, here be dragons, so to speak. But here's the solution, handily and readily provided by PyMC Marketing, the nested logit model. So the idea here is to sort of take the metaphor of branching paths and choices seriously. So the idea here is that in the literature they refer to groups of products as nests of products. So the idea is that when a consumer on the marketplace is making choices between different goods, they first make crude sort of like imprecise choices. So they choose first that I'm going to buy a car rather than a boat. But then once they've decided to buy a car, then they will look at the utilities that accrue to each individual car within that, so Toyota versus Vauxhall, etc. So it's a sort of staggered, stepwise, conditional probability operation. We want to model first that the probability of any given user is a car buyer. And then, once we know that they're a car buyer, the probability that they will choose a Toyota. So to implement that, we again kind of use a softmax type transform, but we have a staggered sort of relationship here. We do the conditional probability and we do the marginal probability, and we tie them together by allowing the conditional probability to bubble up in the nesting structure to inform the marginal probability. So, I mean, I'm not going to go through the code, but like broadly, the structure is the same as before. You set your utility formulas as before, so utility specification for each of the goods, but then you add your nesting structure or your market structure in as a dictionary in this case, and you pass it through to the nested logit model class and you estimate it. And from that you can get so for those who are not familiar with the sort of Bayesian modeling criteria or validation in any sense, what you typically do with a Bayesian model, once you fit it, you estimate the posterior predictive distribution. This is a check to ensure that the model that you have fit can recover the observed data well. So in our case, the observed data is sort of like a categorical field. So it's like what you're really looking for is that it captures the proportion of sort of choices that go to each heating system in this case, right? So both of these models with two different nesting structures seem to recover the data reasonably well, but they have slightly different implications or inferences around the parameter values for the installation costs and the operating costs. You'll note that both estimates are negative, so it should adhere to like a reasonable understanding of human action. Price increases, whether for installation or for operating, have a negative effect on the implied utility that accrues to each of those goods. The different model specification here sort of suggests that with one specification, the installation costs have a greater negative effect than they do on the other model. And so to assess then the plausibility of each model fit, you want to inspect these values. You want to understand these parameter values. How plausible is it that installation costs have such a deleterious effect on the utility of a good? Good. So the problem that I advertised before, the multinomial problem around sustaining plausible counterfactuals, can be solved with this nested logit because it imposes a different structure on the utilities and the comparison among those goods. So what you see here is the same sort of plot as I showed before, but what I mainly want to call out here is that the relative change amongst those goods is now not exactly proportional at 8% for each of the goods. So we have made the model more complicated by introducing the structure, but it now supports more plausible counterfactuals. The IIA problem exists, but it only exists within a nest, not across the nests. And so by adding this structure to the model, we've sort of made the comparison class for consumer choice more realistic. Yes, so all of this is sort of handily supported in PyMC in PyMC Marketing by the introduction of the do operator, which is this sort of Judea Pearl-inspired graph intervention machinery. So you can take a fitted model, this model which is characterized by a set of parameters and observed data. You can take that model and intervene on it. And like I'm doing here, you can either set new values for the observed data, so like new counterfactual values for the future, or you can also intervene and set the parameter at a different level. So in marketing, arguably what you want to do is actually change the parameters. Like you want to change the appetite or the price sensitivity of your consumer base to different parameter values. So if you can run a marketing campaign which will make your consumer base less price sensitive, that's a huge win. You might also want to explore what that looks like under sort of ceteris paribus inference. So this is what I mean when I say that, like, when you're fitting a Bayesian model and exploring the do operator across these models, you're like going from world to world. You're moving from world W here to world star, where you've intervened on the model changed some of the parameters or changed data to explore what the world looks like under those conditions. So this is my broad conclusion. Bayesian models offer a data-informed tool for simulation experiments for ceteris paribus inference. Plausible counterfactual inference depends on compelling world structure encoded in the model. Nested logit models in PyMC allow us to encode market structures for compelling intervention studies, and they also reveal behavioral insights about consumers, unlocking new marketing strategies for you and your marketing adventures. Thank you.
Thank you very much. Very, very interesting. So I would first start with the questions from the slides here over internet. We'll start from the easiest one. Is it correct to think of the nested logic structure as a kind of partial pooling?
As a kind of partial pooling. I had not considered it that way before. But maybe. I don't think that's the easiest one, but maybe, I think. You're borrowing information in the sense that you're imposing extra information on the model.
Okay. Second one, have you applied this method to real use cases? What are the main challenges in real applications, and how do you validate the results?
Yeah, so I've applied it once and the main challenge, to be honest with you, is not the modeling, it's the data acquisition. So like if you want to assess, say, competitors to a firm you're working on, you need to be able to describe, say, the product you're offering, which might be straightforward. You could do that in a data matrix. You indicate all the features you've just delivered over the last 6 months. But describing your competitors well with data that you can validate and support and stand behind, it's a very difficult, very questionable maneuver, which when I tried it, I put together what data I had, and frankly, sales leadership didn't believe me, which I think they were probably right to do, but the data acquisition, I think, is the hardest part, not the modeling itself.
I've heard of using the probit model to avoid the IIA problem, right? How does it compare to the nested logic model structure?
Yes, so I've not explored the probit model much myself, but yes, that's certainly one way to do it. But you kind of implicitly use a multivariate normal distribution in the back end. I think that's a perfectly valid strategy, and POs are open for PyMC Marketing. Another way to sort of avoid the IIA problem without the nested logit machinery is to do a sort of mixed logit model, which is more akin to the partial pooling strategy. It's a hierarchical model where you allow sort of individual parameters on each of the, say, goods or the firms or the actors, so that you can kind of infer taste heterogeneity in the marketplace. And that's another way of introducing kind of, it's a richly parameterized model, which will also avoid the IIA problem.
Okay, now the longest question. In some areas of economics, a popular variation of multinomial logit, MN logit, models involves integrating them with factor models to account for measurement error. The key idea is to study how multiple latent variables influence economic choices. To estimate these latent variables, researchers use multiple noisy measurement and apply factor models. And now comes the actual question.
Okay.
Is this kind of approach, combining multinomial logit models with latent variable estimation via factor models, something you're considering adding support for?
I think I'm not familiar with the literature he's referring to, but just to clarify, the utility function here is a latent variable. So I don't know if that answers the question exactly, but I don't know the literature he's referring to or she's referring to.
Okay, if you want Alexander online put the question, please specify it if it answers the question, or just put another one. So I will open now the round here on the floor. Who wants to ask a question? Okay, there is one.
Great, thank you. You mentioned something about the distance between the worlds, if they're being close to one another, and the relationship to those outputs. What kind of distance function are you thinking in relation to these worlds, or is that just sort of an intuition thing about slightly changing parameters?
It's somewhat of an intuition pump more than an actual distance measure, but these rank orders are sort of like a kind of essentially boiled down to a log likelihood, right? So you could maybe do a distance function over the log likelihood of worlds. So that's distance in probabilistic space, we'll say. Distance in desirability, well, you will be estimating a latent utility score for each of the world states for each of the goods. So if you wanted to compare distance across the worlds and sort of average desirability across the consumer base, you could probably aggregate over the latent utility scores and get a distance measure that way.
Thank you.
Another question. Okay, we still have one question from the audience online. Could you please provide some business cases, questions to apply these tools? I think it's kind of repetitive, but maybe you have something more to elaborate.
Say you're developing software as a service, and you're looking at your current roster of features, and you want to see what will help you win against the competition. You can look at this kind of data to see how effective was the addition of your new feature, timekeeping, to your software as a service application for driving new business. And you can kind of look at those types of questions. So it will help you sort of determine what's an effective species of feature, and then maybe you can make an investment decision that we need to improve this area of the product versus that area of the product.
Thank you. Last chance for a question. We still have 2 minutes. If not, the big round of applause for our speaker. Yeah, last one, but bigger round of applause. Now it's appendix, 1 minute.
Yeah, great talk. Thank you. Very interesting. I'm just curious, on this slide, actually, you have INJ. Is there any extensions that would incorporate like a time dimension so you can have almost like a triple-M approach for like saturation or something? Yes.
So there's dynamic discrete choice models. Again, PORs are open for PyMC Marketing, but like a lot of indices to handle then when you add the time dimension. But certainly there are implementations in the literature. I think you can find some for ML logit, which is a package in OR, but I'm not entirely sure. Thanks.
Thank you again. And